Today I'm going to be talking to you about a library I've created called smaws. It's a AWS SDK for OCaml'. What I'll be presenting is what goes into designing a library and how smaws was built. So a little bit about myself. My day job is working with TypeScript and Node.js, particularly in AWS environments running serverless, something I've been doing for more than 10 years now. I'm quite passionate about learning new ways to build robust software, which has led me to learning about functional programming with OCaml' and how it can be used in different applications. So what exactly is smaws? It's an independent implementation of an AWS SDK. It's short for Smithy AWS. It's a code generator for the Smithy interface definition language, which is used to describe AWS service APIs and generate code for them. And you might be wondering about my motivation for developing smaws. For most developers, SDKs are a secondary concern next to implementing their business functionality. For me, it's because smaws provides a solid project for learning about OCaml'. It's ultimately a code generator, which are easy to get started with for new projects. They provide an instant dev test feedback loop to check your work. You use the compiler as your test runner and your code as a test case. OCaml', I think, is particularly well suited for development feedback loops because of its fast compiler and its type-safe metaprogramming abilities. So why develop another AWS SDK for OCaml'? There's already, I think, at least two. Let's look at how it compares to other implementations. Unlike OCaml' AWS and AWS SM, Smithy's interface definition language lets you generate high-quality interfaces for calling AWS services. It also supports automated compliance testing, and importantly, it uses newer HTTP libraries that take advantage of the effects-based scheduler in OCaml'25. It's also worth exploring how Smithy differs as an IDL from the Boto definitions which are used in the older SDKs. Smithy's model first. What this means is that when you define an API, you're using the concepts and fields as the primary interface instead of low-level protocol concerns like serialization. This makes it protocol agnostic, allowing it to target different schemes for calling an API. It's also specifically designed for code generation with type primitives that map well to most statically typed languages. I'd first like to talk to you a bit about what I think is important when considering the design for an SDK. A good SDK needs to be good for its end users, like that is the other developers who are actually going to use it. But what does that mean? Each developer approaches a library with their own expectations and experiences, but in my mind there are a few principles in common. Developer experience is the main one. Is your design consistent so it's easy to explore? Does it follow the idioms of its target language? Another one is efficiency, so not just good performance, but is it sized well? Also, in principle, validation provides assurance that the code the developer is using has been tested. For an SDK specifically, this means that it's compliant with its service specification. And lastly, documentation is important. And I don't mean just like API reference documentation, but things like guides, tutorials, examples, so that your library is usable by people with different experiences and different needs. All these factors influence the design more than the technical decisions, and they have to be relevant to a wide range of developers. Let's firstly talk about designing consistent and idiomatic interfaces. A logical and straightforward layout helps other developers navigate the code, find what they need, while an idiomatic design uses concepts and structures that are familiar to them from the underlying programming language. The most obvious thing you can do is naming, using a consistent and idiomatic naming convention for your code. Smithy's names are Pascal case, but smaws will translate them into Snake case, which makes more sense in OCaml', like for types and function names, while preserving it for modules and constructors. The clients are also structured to make it easy to find an operation, which each have their own module. Everything else is packed away into submodules to avoid cluttering the main namespace. An AWS SDK for one service could have hundreds of operations in it, like more than hundreds of types. EC2 and S3 are notorious examples of this. So we want to make it easy for people to find what they're looking for when we generate the code for this SDK. If we look at the operation call, there's three main concepts that stand out to be able to invoke a service API. There's the context. This uses this carries the configuration, it carries the authorization credentials, as well as the HTTP library itself. But it can be provided with default parameters to initialize it, with sensible defaults. The operation itself, it wraps up the underlying protocol implementation to call the service API. And then you've got builders like this make list queues function. What they do is they make it easy to construct record types. Some record types can have dozens of optional parameters in them, and with name parameters, we can make that much easier to put together without cluttering the code with lots of nuns everywhere. If I also draw your attention to the above code, you'll notice it feels a little bit more idiomatic, as it looks like synchronous code, even though underneath it's asynchronous. There are lots of types there aren't types like propagating from the asynchronous runtime through to the client code, like you'd get with an older async runtime like LWT. OCaml'25 gave us multi-core and effects to run asynchronous code, but this has spawned many schedulers, like standard libraries, I guess. I chose EIO for smaws, but this isn't something that I should have to impose on the developer, which is a point I'll expand on a little bit later. It's also important to consider error interfaces. I've used polymorphic variants for errors in smaws, as they're more expandable than ADTs, and unlike exceptions, they make clear what errors can be handled. Smaws structures as errors into separate type for each communication layer, the transport layer, the protocol layer, and the operation layer. Instead of flattening them at each layer, they wrap it up as a new constructor in the next layer. So you'll notice HTTP failure comes through as a constructor in the protocol layer, and then the AWS JSON error comes through as into the operation layer. This sort of avoids long lists of constructors in the output type, which is more readable and easier to pattern match. Another important design consideration is avoiding complex language features in the client interface. One of these challenges arose for me when I was trying to make my HTTP implementation substitutable. I wanted to be able to mock the implementation to create compliance tests, and I also wanted to be able to switch out the HTTP library and the scheduler. My first attempt was to use a functor internally, but what I found is that each functor requires another functor all the way back to the client interface, something I wanted to avoid. This is an example of what my ideal interface would be. You have a simple module type, HTTP, and then you have an implementation for each, say, HTTP library or each scheduler. Using first-class modules let me hide the underlying implementation from other complex language features. My first attempt simply tried to store the module and an instance of its type T, but this doesn't really work. Type T doesn't really exist in this context because it's part of a module type which is stored differently from its module implementation. My second attempt was to parameterize it. We can store the module as part of the context value, but we can't return it because type T is locally abstract, and it would escape the scope of its function. My third and last attempt found a solution. So if we parameterize the locally abstract type and the module in the function interface, we can then also simplify this further by implementing a factory function, this make down here, that hides the first-class implementation from the end developer. Now that I could switch implementations, I also looked at supporting other HTTP libraries. I've been able to get it working with the HTTP cats library using the meow scheduler. Those are words I didn't expect to say. Which you can see in the example below, showing almost identical code except for the context creation. With these simpler extractions, the developer's code becomes easier to reason about, ensures that code doesn't carry complex types from the library, and lastly, it works better with code completion. First-class modules and functors don't code complete very well. So the next one I wanted to talk to you about was efficiency. So efficiency could be taken to mean a couple of things. Raw performance is usually the first idea that comes to mind, but I also think this means using resources effectively in your application. I mostly work day-to-day in serverless environments, so when I'm talking about efficiency, I'm mostly thinking about how long the code takes to run and the impact on response times for customer-facing APIs. The performance of these applications is bound by the network, but it can easily be affected by how long the serverless container takes to start up. This factor directly relates to the amount of code deployed for a particular application. So in these environments, deployment size matters. In serverless environments, code is loaded from object storage on demand. If there's no existing container running, what's called a hot container, the user experiences a cold start, which is from the container loading up. What this directly translates to is larger code sizes give longer cold starts. Build and deployment times also suffer, and this isn't a problem confined to serverless workloads. If you're dealing with containers or deploying even like whole instances on images, you'll have the same problem. What this means is I look to use smaller, more focused libraries, and I lean on the compiler to remove unused code, which I think is easier said than done with OCaml'. The standard compiler seems to work in terms of compilation units, which are individual ML files. If a unit's not referenced, it'll be thrown away at compile time. So this is what I try and optimize for. The key to understanding this is how code is referenced by other modules. If we use something inside a module file, we'll pull in that entire file and all its transitive dependencies into our program. But we don't want to have to put everything in separate modules to avoid that because it makes it harder to navigate the code as an end developer. Thankfully, there's an exception to this rule. If you simply alias a module and then only reference the alias and nothing else in the surrounding module, the surrounding module isn't pulled in. The compiler literally just reaches out for the thing that's been aliased and pulls that in directly. We can exploit this to group together mutually exclusive modules, such as HTTP implementations, in the same place without forcing the end user's code to include both. You'll see it more clearly in these examples. The first line is just like a simple module alias. The second one is a functor. Functors get expanded in the scope, so if you reference that second line, you'll get the whole http.ml file as well. And same with this one. If you narrow the type interface, it causes the whole module to be pulled in. smaws takes advantage of this to not pull in unrelated code. A good example is like some of the underlying protocols use XML. If you're not using one of those protocols, you don't want to have to pull in an XML parser. You can also see the value of this approach by looking at two different HTTP libraries. This is the dependency tree for two libraries. The ones at the bottom is the common ones. The one on the left is HTTP cats, which is uses the meow scheduler, and the one on the right is HTTP on EIO, which is the EIO scheduler. There isn't much in common with these. If we didn't use aliasing, we'd pull in both sets of libraries into any client program. We can separate them into separate libraries, but when you're grouping modules and splitting them up, this isn't always reasonable. There can be lots of little permutations which don't make sense to put into their own library. The last one I wanted to talk about was deserialization performance. Deserializers have to deal with data from external data sources. They need to handle invalid data while still executing fast. Parser combinators are quite commonly used in functional programming for deserialization, but this comes with extra allocation overhead. We could use exceptions, but we don't want to lose the benefits of a result type. smaws uses a popular approach where exceptions are thrown for errors internally, but they're converted to result types externally. We get the performance benefits of stack unwinding while still being able to provide useful errors with a full deserialization path of where something went wrong. Another important design principle is ensuring the code is compliant and validated. smaws is still new. It can be made much more usable with the assurance that the implementation has been compliance tested against the underlying specification. Smithy allows for HTTP compliance tests, which we can use to validate the generated SDK code and associated libraries. There's two types of tests. Request tests ensure the SDK sends the right HTTP request, checking the URI, the body, the headers have been generated correctly, and then response tests do the same in reverse, checking that the responses have been passed correctly. This is an example of a Smithy request test from the AWS JSON protocol test suite. It's validating whether a union type, which is roughly equivalent to an ADT in OCaml', is correctly serialized in the body of an AWS JSON request. This request is transformed into something like this unit test. I know there's quite a lot going on here, but we can see that similar concepts. We have the input up here. We see it being compared to the body serialization down here, the method, the URI, et cetera, et cetera. This type of test is really good for automation because the tests are generic and can validate any HTTP-based protocol. It's also really easy to keep them up to date by regenerating them from the IDL. And then lastly, like the principle I wanted to talk to you about was documentation. And I know this doesn't sound like a design principle, but you can provide basic API reference documentation with your library. Smaws has a HTML to ODoc converter, which converts between the Smithy like HTML format into the ODoc format. But the links between fields and types and operations will require like significant internal uplift to build like symbol tables to actually be able to link between, say, a field and a module, or a module and a type, or what have you. But also beyond API documentation, there's some like getting started guides. This could be improved with more worked examples and tutorials. Maybe we'll take a little bit of a look inside Smaws now. So Smithy itself, it has a fairly comprehensive type system that maps pretty well to OCaml'. Primitive types and collection types are pretty straightforward. They don't require much else except one external library, which is ptime for timestamps. Even composite types like structures and enums and unions map relatively well. An enum is like an ADT with 0 arguments. A union is like an ADT with a single argument of a different type. And then in the service layer, you have operations, services, and resources. Services kind of group operations together, and then resources group operations around like a particular, I guess, like a REST resource, if you're thinking in terms of REST. So how is Smithy described? All the type definitions, the operations, the services, the resources in Smithy are described by a shape. But the flexibility in Smithy comes from its trait system. These let the designer extend the shapes through key value pairs that add additional information like field optionality, range constraints, documentation, validation rules, how the code is generated, amongst other things. With this relatively simple design, the code generation pipeline is actually quite straightforward. A Smithy JSON file is just a list of shapes. We parse it into an AST and then split it up into different types, and then just generate the code for each of the modules, like the types module, the operations, the different serializers and deserializers, and like a sort of a client interface, which is the module name. The code generation pipeline itself started relatively simply. It's concatenating strings together and compiling them. This is great to start out. It's very fast. It's very easy to understand, but it does break down. Finding issues becomes harder as regressions creep in. Even implementing tests to combat this is challenging because the code generation process becomes more brittle. The current system uses ppxlib to generate AST. It's easier in some ways because ppxlib provides these builder functions to construct the different parts of the OCaml' AST, and it smooths over the AST versions, and it sort of prevents you from making really silly type inconsistent errors. But the naming conventions can be a bit inconsistent and rather cryptic at times. And the type system itself can't prevent everything. I think you have to move to something like meta OCaml' to generate like truly compliant code. Just a last note on meta programming, like the loop itself with Dune. I found it's relatively easy when you're dealing with single files. You define a Dune rule that generates code, and then use mode promote to pull it into your project, and then inspect the generated code. Multiple files, somewhat more difficult. Maybe we can generate the Dune files ourselves. It's something I haven't quite got to yet. I'll show you a quick demo. Let me just go up here. Okay. No. Run this. Okay, so so what I've got on the right here is the code for a Lambda function that's written in an OCaml'. This has been compiled down to run on Amazon Linux, which is like a customized version of Linux that has a fairly old glibc. What we have on the left is our Lambda function. It's listening to a queue called employee changes. Let me just run this through. This Lambda processor is taking the messages that come in off this queue, and then it's writing them to a DynamoDB table. Sorry, let me just jump ahead a little bit. So if we just take a look at the code on the right for a moment, up here at the top, basically we get an event, which is like a list of messages. That is then processed, but with an EIO fiber. So we actually map over the list of messages that come in and create a fiber for each one. That we deserialize it, we then convert it into the DynamoDB input, call the operation, and then if there's any errors, we actually capture the message IDs and return them. Because we're dealing with a batch of messages, if we can just return the message IDs that failed, we can actually prevent it from reprocessing the entire batch. Now if we jump over to SQS, this is a message we're going to put into the queue. Now that will have been sent to the Lambda, and you can see like our existing record here, and our new record has been added to the database. Also, if we take a quick look at the logs, there we are. Yeah. We can see, based on the log statements in our code, we can see the message that's come in. This is the SQS format. We can see the deserialized payload, which is the message that we sent to the queue, and then we can see the result of writing the message to the database. So this is what's been put into our DynamoDB record. So what I'll do, switch back to here. So let's just talk a little bit about the current state of smaws. One way of examining its completeness is to look at the services it currently supports. So on the left here, you've got all the different protocols that are used to create AWS services. At the moment, we implement the AWS JSON protocols. These cover about 36% of the services, and a number of like really important baseline services like SQS, DynamoDB, CloudWatch Logs, EventBridge. The next one you would think I would try and implement is REST JSON because it covers like more than half the services. But a lot of those services are ones that you would not normally use in a production application. The ones that are actually interesting are hidden behind the AWS query, the REST XML protocol, so things like S3, CloudFront, IAM, really important, SNS, which is like a topics, like if you're publishing to topics. One of the complications of supporting some of these protocols is that they all have their own like little serialization things. REST JSON is quite complicated. It can actually map things into headers, and like your import record can actually have like stuff pulled out of it, and then when you actually serialize it, you don't put all the fields in it because they've been put, say, in the header, or they've been put in like part of the URI or something like that. If we look at the compliance tests themselves, the HTTP request tests, we've been able to, I've actually spent some time getting that working for all the AWS JSON ones, so we can now say we're compliant with those. The response tests we don't currently implement, but there's far fewer of those, but they're relatively easy to get going. I think that'll probably be one of the next things to like round off that piece of work. There's also like the question of what comes next. I'd like to expand the protocol to support, like as I mentioned, and add other authorizers as well. So at the moment, we just have a very basic authorizer that uses IAM access keys, which is not the most secure, but it's enough for using AWS Lambda. I'd like to be able to support, say, running on EC2 instances, SSO authentication, so you can actually sign in a work environment. I've also talked about supporting other schedulers and HTTP libraries. I'd like to actually continue doing that, but also just developing better samples and applications and documentation. So this is makes more sense for people who are sort of coming to it for the first time. So in the process of working on smaws, I've created a couple of other related projects. There's OCaml'25, which sort of generates CloudFormation bindings for OCaml. And there's OPAM cross Lambda, which is a cross-compiling OPAM repository that uses Zig. If there's anything I wanted you to take away from this, it's creating libraries for other developers is a challenge. You're balancing lots of different technical constraints while thinking about developer experience, efficiency and performance, validation, documentation. The choices you make in your interface and error design affect its usability, including things like what automated testing you supply with it. For smaws, the Smithy IDL provided a really solid foundation to achieve these goals for an AWS-based application. Thank you.
Thank you, Chris, for the presentation. Any questions from the audience?
Thanks. Thank you very much. It was very impressive. I guess that Dune parameterized library will fix some dependency injection feature, but I have two questions. The first one is, did you try to abstract using effect instead of tower of functor application? So you can just give an handler in a dedicated library that will call what you need and give you the management of your control flow, so you don't need to have a lot of functor application to make dependency injection on top of your what you need as a dependency. And the second question is, when we are working with AWS, we can be stuck with AWS, which can be very expensive. And since I guess that you have a lot of signature that define the way that you interact with your set of services, can we imagine something which can be more cloud agnostic to share signature between different cloud providers in order to use it, for example, to deal with other very expensive services like Microsoft Azure or Google Cloud Platform and stuff like that?
No, they're good questions. So something I was explaining, when you're dealing with different HTTP libraries, you can just bundle them up as a first-class module and then just pass that into the implementation. Because the effects don't add anything to the interface, you can just pass in whatever you want, and it pretty much operates the same underneath. That's the way I've tried to solve it. I mean, I did try and use functors first because that's what the dependency injection is like the most traditional, I guess, use of them. But they're probably not actually that necessary for this application. In terms of like abstracting over the AWS interfaces, that's a really good question. I build AWS stuff day to day. The actual need to move between cloud providers doesn't come up as often as you would think. There are certain companies who like to move between providers. I find it's not really necessary. AWS is expensive. And I think if you were moving away from AWS, you would probably just move to on-prem. Rather than to another cloud provider. The model is expensive if you have a very flat workload. The reason I've found serverless to be very useful is because when you're exposing like a website, it's actually a really spiky workload. And although you're paying more per request, if you don't have heaps of requests, or your requests are just maybe in a short part of the day where you only need you might need a quick ramp up and a quick ramp down. The costs are relatively minimal. Also with things like DynamoDB too, it's a fully managed database. You don't pay for things that you don't use. You just pay per request, and if you're only storing a certain amount of data and you actually think about what you're doing, it's actually not that expensive.
Okay. Thank you.
Any more questions? Okay. Yeah. Thank you, Chris.
Thank you.